All right. I guess it's a thumbs up. The projector is not on.
Oh, sorry. There we go.
Okay. Welcome, everybody. I was expecting welcome to Tech Academy. I don't know anything what to say. All right, so I am Julio Barros, and I'm going to do an intro to machine learning. And the idea here is that this is a big overview of what machine learning is and how it fits into the picture, and maybe some of the tools that you would use if you're interested in machine learning stuff, just to give you a taste of this. We will do this overview. I have a quick demo to just walk you through some steps for how you would do this, and then we'll have Q&A until it's time to go. But you can please feel free to ask questions along the way. It's perfectly fine. Actually, I would prefer that. Me, again, my name is Julio Barros. Maybe a good way to reach me would be on Twitter at Julio Barros. I'm a consultant here in Portland. I'm a machine learning engineer. I consult for other companies. And I also lead two related meetups, the Deep Learning Meetup and the Probabilistic Programming Meetup. And they meet right here. So if you found your way here and you want to come join that meeting, those meetups would be fantastic. Everybody's welcome to any level of experience or any kind of interest. Okay, so why machine learning? Machine learning is something that's gotten a lot of hype, and I think it's underappreciated. Both overhyped and underappreciated at the same time, depending on who you talk to and what their expectations are and what they know or what they want to do. A lot of people fall into one of those two buckets. This is a quote a while ago from Jeff Bezos, who says, AI is a horizontal enabling technology. It has the power to improve every business, every government, every organization, everything. Basically, there's nothing that cannot be improved with machine learning. That's maybe a little bit on the hyping part of it, but I believe it's true. But I have a vested interest. I'm a consultant, a machine learning consultant. This idea. I think we can make everything, improve everything with machine learning. We can't necessarily, though, have human-level intelligence. Everybody kind of jumps to this extreme of human-level robots that are going to kill us all or something like that, or put us all out of work or anything. I don't think that is realistic, but I think we can improve a lot of processes with machine learning. And then machine learning, AI, and deep learning in particular have gotten a lot of hype recently. And the way I think of it is that AI, deep learning, we'll talk about what that is a little bit, is a kind of a subset or a type of machine learning. And machine learning is a type of AI. They get all combined, and people use the words interchangeably sometimes, but that's really how I think of it. So AI is the study of intelligent agents, and for me, I think it really is getting approximate answers to uncertain conditions, especially when you cannot compute the answer exactly. So think of, it used to be that checkers, playing checkers was AI, because the checkers board was so complex that you could not calculate the answer. But as computers got faster, then we can calculate a checkers board. So that is a solved question. So then we moved on to chess, and then Deep Blue beat Kasparov back whenever that was, and so that became. It's not solved. Chess isn't solved, but there are machines that play chess really well. And so we moved on to games like Go. And the search space for Go is so huge that I can't even make up the numbers. It's just the biggest number you can imagine, right? So you can't calculate a Go board directly, so you have to have a bunch of strategies to come up with a reasonable answer very quickly based under uncertain conditions. So that's what AI is. AI is a study of that process. A lot of these definitions aren't really super clear-cut. There's not a clear line. It's just kind of this general idea. And then when we talk about AI, there are a lot of, you can talk about artificial narrow intelligence, which is a program that does one thing really well, right? It plays Go really well. It would not play, or it plays 19 by 19 board really well. It probably doesn't play the 21 by 21 very well or 17 by 17 very well at all. If it does one thing, it does it really well. Artificial general intelligence is, I think, what we're all afraid of. If they're going to take over our jobs or whatever. It's like the idea of an AI that can do a lot of things really well, and they can do it so well, do it well at a human level. And then people say, if we ever get there, that things will start learning how to improve themselves, and so to the point that they learn faster and better than we ever imagined. And then we get artificial superintelligence, which is a machine that knows can be way better, smarter than us, way faster than us, or whatever. I don't think that anything of that is realistic or nowhere near anything like that. But that's just like what people mean when they say, artificial general intelligence or superintelligence. So a subset of that, of all that, is machine learning. Machine learning is just a program that learns from data. It learns from data and makes predictions. Some of the classic tools are linear and logistic regression, kind of decision trees and ensembles of decision trees. And we'll talk about what they are a little bit as we go on. Neural nets, which is deep learning, and probabilistic methods, which are ways to calculate, ways to use probabilities and probability distributions to figure out, to get a prediction with some level of uncertainty in it. We'll talk about that a little bit more. And then deep learning, since that's like the big thing, it's gotten a lot of hype. It's this idea of having biologically inspired neurons, but the neurons are really, really simple. They have nothing to do with biology anymore. They were just kind of thought they were it was an analogy from the 50s. It really doesn't like track or mean anything today. So neurons has really very little to do with biology. But starting in 2012, deep learning has been able to make a lot of big strides in what are called perceptual tasks, which are like looking at images and classifying images, listening to audio and classifying or figuring out what's in the audio, things like that. And they get a lot of criticism for being black box algorithms. Basically, it's really difficult to really understand what they're doing. You kind of just take a bunch of data, you throw a bunch of data at it, you teach it, you tell it to learn, and then it starts giving you predictions, but you don't really know why, and it's kind of hard to understand what it's doing. But people are working on that also to both have them learn with less data, because they need a lot of data, have them learn faster, because they need a lot of compute power, and then have figure out ways to figure out what they are doing. Any questions about those different categories?
What do you use the black boxes?
Hmm?
Where do you use it, the black boxes, the algorithm?
The idea of saying that something is a black box algorithm means that you can't see in it, you can't see inside, you can't see what it's doing. So the neural nets are used everywhere for a lot of different things. But the idea is that I can use it to analyze images coming off the camera, but I don't know exactly what it's doing. It's just giving me predictions about what it sees, but we don't know why exactly.
Uh-huh.
Okay.
What's the neuron? Is it just like a little CPU?
I think I have a slide later. We'll talk about that a little bit later, okay? So I do think that machine learning is applicable everywhere. It's we use a heuristic. And a heuristic is, if you're calculating something specifically, if you're reading and writing from a database, fine. You don't need machine learning for that. But if you would like to predict something, or if you'd like to kind of make a decision on whether something is valid or invalid or good or bad or going to make you money or make you lose money, those kinds of decisions, something's going to take a long time or not take a long time, those heuristics, those things those rules of thumb that you are currently encoding in your programs, you can use machine learning for. So anything like recommendations, forecasting, ranking things, anomaly detection, is what you would use machine learning for. And people think of it as user-facing, but there's also consider all the business processes, all the internal stuff that you don't see. I don't know where people work or what they do or what they're interested in, but you could have an AI that plays a game for you, or you could have an AI that decides whether something is fraud or not, or you can have an AI that lets you know whether it's a good time to take vacation or not, based on your human resources. All right. Machine learning, the problem types, the types of questions. So I'm going to talk a little bit later that the idea is wherever you want to use it, you've got to phrase the question in a machine learning way. And machine learning really is focused on answering specific kinds of questions. One is we call regression, is where you want to predict a continuous value. You want to predict a number, right? So the price of a house, that's a number, that's a regression. How long something will take, that's a number, that's a regression. The other big kind of problem is a classification, where you're predicting a label on something, so it's discrete values or discrete labels. If you want to say whether something is fraud or not, whether something is a cat or a dog, whether something is a hot dog or not a hot dog, whatever it is you're trying to predict. Those are labels, those are classifications. There are also things called, those are your most common kinds of questions you can pose. You can also pose questions about representations, which give you like a compressed feature set, or you could use for clustering. So you don't have, what you're trying to do is find group things that are similar together. And then you're trying to figure out what makes them similar in your system. And then lately there's been a lot of work too in generation, which is also part of machine learning, where you teach a system maybe, the clearest example of this would be maybe music generation. You can take a system, show it a bunch of Bach, and then it'll generate something. It'll learn what a Bach, piece of music is like, and it'll start generating music that's in the style of Bach. That's gotten some progress and some really interesting results with that too. So there's all kinds of things like that you can do.
You say like the Shazam app that identifies songs would be generation?
No, I think if you're identifying songs, that's more classification. But depending on how they do it, it may be machine learning or not. It may be a specific algorithm they have, or maybe kind of probabilistic, or we may have some sort of different ways of doing it. Yeah, so identification is classification. And then the learning strategies, you have to get a bunch of data, and then your problem can be supervised. If you already have labels, if you have data with prices, and then you're trying to predict prices, you get all of the old deals, and the label is the price for the old deals, and then you use that information to train your system to get, so that it predicts the new price. So you have those labels, you have those prices, that's the supervised kind of training. The unsupervised is really more clustering, where you don't have, so the example I'm going to use is real estate, housing price prediction. So let's say you don't have the prices, but you want to group houses into being similar or not, so maybe on the number of bedrooms and the number of bathrooms or something like that, that tells you whether it's a big house or a little house. And so you don't have preconceived labels for them, or you don't have the price information beforehand, but you want the system to find a way to group similar things together. So that's what unsupervised training is. And reinforcement training is the idea that you have something in an environment that is going to take actions in that environment, and it's going to try to maximize something, but it doesn't get the labels, it doesn't get the response right away, it gets it a little bit later. So you could think of it as a stock trading robot or something that's going to make buys and sells, but it's going to take a little while for it to decide whether that was a good buy or a good sell. Or a robot that's trying to walk down trying to navigate its own, trying to navigate somewhere on its own, and it's going to make different turns, so we don't know how those turns will work out until it makes a fatal mistake or until it gets to its final destination. So it's a little bit like supervised because there is a reward, but the reward or the goal is not immediate, it's kind of much further down the road. And then a lot of people say, well, isn't this just statistics? Isn't this just a new kind of statistics? And it is. It's a new kind of statistics, and it's related to old statistics. I like to think of statistics as being, or analytics, being broken down into descriptive, predictive, and prescriptive. And descriptive is something that tells you something about the past, really, because what you're doing is you have a bunch of house prices, sales, information on housing sales, and then you say, well, what's the average price of a house in Portland? And that is a descriptive statistic. It just tells you the average price is $400,000. Okay, so that's cool. The predictive is like, well, what are houses going to sell tomorrow? What are houses going to sell for tomorrow? Or what is this particular house going to sell for? You can use descriptive. You can use like the mean as a prediction for tomorrow. Like if you have a little shop and you're like, well, I sold 100 hamburgers today. How many hamburgers am I going to sell tomorrow? Well, a really good guess is the same as you sold today. So you can just say, well, I'll just buy 100 hamburgers because that's what I'm going to sell tomorrow. So that's how you would use descriptive statistics to predict something tomorrow. But if you were thinking, well, it depends because tomorrow is a weekend, or there might be an event in town, or the weather's really nice, and so on nice days there are more people that visit my cars and stuff. So now you start trying to make predictions about tomorrow, and then that is what moves you from statistics, from traditional statistics, to machine learning. And then prescriptive is the idea that you have a machine that tells you what you should do so you can sell more hamburgers. That doesn't really exist yet today. Like, but people are working on that. You know, what could I do? How do I change my business? How do I change my decision process so that I make even get closer to my goal or get more reward tomorrow? That's prescriptive. That's a little bit cutting edge. That doesn't really exist. So that predictive descriptive is kind of the difference between statistics and machine learning in my mind. And again, there's no clear line or anything. It's just kind of a working definition. Okay? Languages for machine learning, you can use any language you want. Every language is at some level kind of equivalent, and so it doesn't matter. What does matter is like the tools or the libraries the language provides and how the culture, you know, people, what they learn in school and stuff, and what they end up writing in and writing articles and stuff about. I would say that the most popular languages right now for machine learning type work would be Python, R, MATLAB, and anything else, everything else, Scala, you know, C#, everything. I'm sure there are machine learning libraries for whatever language you want to do. In school, if you're an engineer, this is kind of my rule of thumb, I think. If you're like an electrical engineer, your professors probably learned MATLAB back then, and so they're teaching their classes in MATLAB. So if somebody says they're MATLAB, I say, yeah, you're probably an electrical engineer. If you're a statistician, or like a life sciences kind of person that's learning to do a lot of statistics type work, your professors and the people you're learning from probably learn either S or SPSS or whatever, and they might be moving to something called R, which is a fantastic language for statistics. So that's the most popular one. And if you're a programmer or a computer scientist, maybe, you're probably kind of started off with more general purpose language like Python. And Python has a lot of libraries now. A lot of support for machine learning. So those are the ones I know. I'm sure that whatever your favorite language is has libraries, but I just don't know what they are, right? So I'm going to use Python in our examples. And the thing is, why Python, or what is it about, what parts of Python make it really powerful? It's not the language itself. It's actually these three libraries that somebody wrote, and they wrote them in happen to write them in Python. One is NumPy, which is native arrays. If you know a language, a lot of languages have so the machine learning and statistics in general, it's just going to use a lot of computation, a lot of CPU power, you know, or GPU power. So you have to do a lot of math. To do that much math, if you have a language that has object-oriented numbers, then you're going to lose some performance there. So it's useful if you have native arrays. And native arrays are just like really binary computers kind of math, numbers and math that the system does. So NumPy gives Python that ability. If you, Python is fast enough for machine learning because NumPy actually does all the heavy lifting in native numerical operations. I think I'm rambling a little bit, sorry. There's also then, on top of that, there's something called pandas. And pandas is another data structure or library that gives you this data structure that lets you manipulate tables, kind of like a spreadsheet of data at a time. So you can drop columns, add rows and stuff. So you're kind of looking at this big table, kind of like a spreadsheet kind of thing. And then scikit-learn is this other library that has a bunch of machine learning algorithms and utilities in there. So whatever language you want to use, you probably want to find something like that in that language. Probably native arrays is probably important because you're going to have a lot of data. You want to calculate it quickly. Something to help you manipulate that data that in kind of a tabular way is really useful. And then something that has the machine learning algorithms. Okay. The machine learning process. The whole thing is you have to, the key thing. So all the tutorials, all the books, everything out there, they really focus on building and training a model. Because that's like the core of like, what model should I use? How do I train this? Why do I build it or whatever? But I think it's really important to realize that the first step is really figuring out what the problem is and defining it. You know, like what is it I want to predict? Like what exactly do I want to predict? And then what kind of performance do I need? You know, and everybody says, oh, well, it's got to be exactly right all the time. It's like, yeah, that's not going to happen, right? So what kinds of errors can you tolerate? What kinds of failures can you tolerate? what kinds of precision, and so on and so on. But if you're trying to predict something like in a medical situation, you have very different requirements than if you're just trying to predict a good move in your game or something. One is really critical, one's not critical. One has room for one kind of error, the other has room for other kinds of errors. Then the next big step is to find and prepare your data, which is really always takes way, way more time than you ever imagine. If you're doing this for business, you'll have, the sales data is over here in this crazy format, and it's dirty, whatever, or at least, like it's never entered in the same way, and the CRM data is over here, and then the website data is over here, and you've got to like find it all and figure out how to clean it and stuff. That always takes way more time than anything. Then you build and train a model. You pick a model that you like, an algorithm you like, and you train it to make the predictions you want to train. You see if it's good. If it's good, you're good. If it's not good enough, you come back up here and then like jump up and either redefine the problem or find more data or try a different model or whatever. And you just keep looping like this. When you find something you like, you put it into production. But then you've got to manage it because the world changes. So just because something's making good predictions today doesn't mean it'll make good predictions next week or next month or whatever. So you've got to then find systems to manage it. So, all right. So the big thing, I always like this big data prep. Don't underestimate the data prep. Don't underestimate defining the problem. Defining the problem is the big thing, right? And then everybody complains about data preparation. It takes up all the time, and nobody likes it. I like it. I like it. Most people don't like it. It takes up all the time. Okay. And then a big thing, though, to keep in mind is machine learning, the performance. In a lot of cases, it's human level. But what that means is that it doesn't mean it's perfect. Humans make mistakes. Humans make a lot of mistakes. Humans make mistakes in which they don't agree with themselves. If you ask them the same question twice, they'll give you two different answers. Experts will disagree with other experts. And so it's really hard to figure out how, it's not hard. You really have to think hard about what kind of level your problem really demands, and then what you're going to do to handle it when your program makes a mistake. If it's going to make mistakes, so what do you do there? Same type of thing, probably the same kind of thing you would do. What happens when a person makes a mistake? You have other checks and balances in the system. So instead of focusing on replacing people right now, we should really focus on augmenting them, on getting them tools so that they can see things much quicker, and so they can make the final decision about whatever it is you want to do. But yeah, that's all. So think hard about the performance. Also, there's a lot of interest or a lot of recent attention to fairness. Everything is biased, and every algorithm out there, people talk about machine learning or AI is biased against this or biased against that. And that's true. That's true, but then everything is biased. And a lot of that comes from the data being biased, so you really need to think carefully about what you're trying to do, why you're trying to do it, who does it help, and then who does it hurt, and where the data came from and how you got the data. If you don't have data on a particular segment of the population, any predictions you make for them really run a risk of being biased against them because you just don't know. You've never seen that kind of person before. So your model may not, will probably not work well in that situation. So how does that affect them? So keep that in mind. And then interpretability is the idea of if your model makes a decision or makes a recommendation or makes a prediction, why? People are going to want to know why. If you turn down somebody for a loan, they're going to go, well, why did you turn me down for a loan? So you need to keep that in mind when you do your models and figure out how you're going to answer that question or what is a reasonable answer to that question. And again, the system will fail, so you need to know what the failure modes are likely to be and how you can handle that. This script is so quiet. Are you guys bored? You have questions? Okay.
When you
Yeah.
say why did it make that decision, do you mean how the weights differ?
Yeah.
Okay.
No. Yeah, that's a good question. That's a good question. And I have a whole nother long talk on that. What does why mean? Yeah. And I think the programmers and the technical people here, us, we tend to say, well, how do the weights differ? But that's not necessarily what the person who got turned down for the loan wants. They don't necessarily want to know that your weights, we didn't give you the loan because weight 3 was 5. You know, like that doesn't make any sense.
But you can translate that to something physical and real, right?
No, you cannot. You can try, and there's some things you can do. I think when I give the other talk, my little radical stance is that you cannot do that, but you need to, and so we try to figure out what you can do to compensate for that. So there's a long reason behind it.
So at the beginning of the talk, when you said understanding what the algorithm or what the black box is doing,
Yeah.
you didn't just mean what the algorithm is doing, because you know what the algorithm is.
Yeah, let's talk about this a little bit more. So you know what the algorithm is doing, but I feel like that doesn't necessarily answer the question as to why it's doing that. But we can talk about that a little bit more. Okay? All right. But just be aware that people are going to ask you why. Your boss is going to ask you, why should I trust this? Why should I order 150 hamburgers for tomorrow? You know, and you just need to have some kind of strategy for answering those questions. All right, so we are going to do an example. Oh yeah, so this is just a quick example. This is a data set of home sales in Washington and King County, which is a county that surrounds Seattle. And it's data from May 24th to May 2014 to May 2015. You can get the data sets here from Kaggle. Basically, it's 19 features and 2,100 observations. In a regular, real data science kind of problem or situation, we would really examine the features, try to understand what each feature is and what it does. We don't have time for that right now, and I actually don't know what the features are. Like, really what they mean, I'll show you what that means in a minute. So I know this is really small, but there's the ID of a house sale. That doesn't matter. It's just like some particular ID. There's the price. That's our target. We're going to try to predict the price. But there are things like bathrooms, the number of bathrooms, the square foot of a lot, the date of the sale, the number of bedrooms, the square foot of the living space. There are things, though, like waterfront is whether it has a view of the waterfront, and view is whether the house has been viewed. So my question is, I don't know when they collected this data. Like, nope, some houses were viewed, some houses weren't viewed yet. I'm not sure. I don't know. That's kind of thing you really need to tease out for real. But we're just gonna go with it here. There's another one, condition. How good the condition is overall. That's all the information I have, right? But I don't know who made this determination or how it was made or where it came from or anything like that. And there's another one that's called grade, which is the overall grade given to the housing based on King County grading system. Again, I don't know how that differs from condition. I don't know who did this or why or under what process or whatever. So those are really important questions to ask if I was really going to do this for real. But for the purposes of the demo today, I'm just going to ignore that and just take the data the way it is. And we are just going to use the data that we got from Kaggle. They've already collected it. They've already cleaned it. They've already said, this is the data. So we're not defining the problem other than predicting price. You know, we're not defining, we're not collecting data. We're not cleaning the data. We're not doing any of the hard stuff. We're just going to do the modeling stuff. You know? Okay, so approaches. If your boss said, hey, we need to predict housing prices for these new houses. They're going to go on sale. We need a system to do that. Well, you could do this with some hand-coded if statements. You could get a realtor and go, well, how do you know how much a house is going to cost? And you go, well, if it's a 3-bedroom house, it's going to cost this much. If it's 3 bedrooms and 2 baths, it's going to cost this much, whatever. So you could create a bunch of if statements in your code that do that. Right? So that's a manual kind of approach to doing that. Right. Anybody see some challenges with that? Okay, there are a lot of challenges with that. One, you need to know what if statements you need. 2, the if statements don't change, so you need to change them based on the data. So you need to sprinkle some machine learning on this, right? So the first approach that everybody does for every problem, and it's probably because it's really a good approach for everything, is linear regression. And the idea is you go back to the old equation of a line, which is y equals mx plus b. B is the intercept, x is some feature that you have, and then m is some slope for that feature, or some weight you're going to give that feature. And that's for a one-dimensional line, for a line, but you can extend that to any number of dimensions. And come up with a formula like this that gives you the price of the house. And it is something like some number times the number of bedrooms, some other number times the number of bathrooms, some other number times the size of the house, plus a base thing because no house is less than some intercept, and that gives you the price. This is linear regression. It's the most common. It's really, really powerful. It's really useful. It's a good baseline. It's a good place to start. Do we understand what that means? Okay. If you go to someone, if you go to your boss, or if you go to a realtor, and the realtor gives you these weights, then you're not doing machine learning, you're just implementing a formula. That's fine. If you learn these weights from the data, if the system learns the weights that minimize the error based on the data you give it, then that's machine learning. Right? So that's the most classic, straightforward approach, useful for many things. Okay.
I don't know if this is.
Sure, yeah, sure.
How is machine learning different from just straight up regressions? Why is it not called statistics? Why is it called machine learning?
That's a good question, and that is right at the border, I think, right? So this is like the kind of, this procedure is something you would use in statistics class, but it's also like the first procedure you use in machine learning. So it's right where they overlap, yeah. The next thing you could do is use a decision tree, where it's very similar to the rules that you created before, except instead of you manually creating the rules, the system will look at the data and then start creating rules based on what it sees, a little decision tree, to make the decision you want, to make the prediction you want. So it'll look at the data and it'll decide to look at the grade first. And if the grade is greater than 8.5, then it'll look at the size of the house. And if it's less than a big house, then it's going to say, well, this is the value of that house. If it's a big house, it'll give you that's the value. If the grade is less than 8.5, then it'll look at the latitude, where it is, and then it'll give you two prices. So this is a very small decision tree, but you can have a decision tree algorithm go and create this decision tree, this little set of if-then statements automatically for you, and then you can run any new houses through the tree to get predictions. Okay. This is a very small tree, but then does that feel like machine learning, right? Because it's not statistics. The machine is kind of learning some rules based on the data. You can use ensemble methods, and these are really powerful. And the idea is that instead of having one big decision tree, you have a bunch of smaller ones. You have a lot of them that look at different parts of the data, and then they all make predictions, and then you take all the predictions and somehow combine them, and you make the final prediction. These are really powerful, and they work really, really well. So this is another great way to go. Okay. And then you could try to throw deep learning at it. And deep learning, I forgot who asked. Yes. So with deep learning is actually really similar to linear regression. Each node is not each neuron is not like a CPU or anything like that. Each neuron is this formula, where it's going to have some weights times some input, plus some weights times some input, plus a bias, and then each node, and that's going to pass that through a nonlinear function, and then each node is going to do that calculation. So this node is going to learn that calculation. It's going to learn its own set of weights, and then this node is going to learn its own set of weights, and so on. It's going to pass its prediction to the next layer, and then this layer will do the same exact thing and pass its predictions here, and then this layer will do the same thing and pass the predictions out here, and then out here you'll finally get the final place. The way deep learning works is that you start out with a bunch of random weights, you shove some data through it, you figure out what your error is, and then once you have an error and you guessed too high, you go back and adjust all the weights that made you guess high, you adjust them down. All the weights that made you guess low, you boost them because those are good weights, and then you do the same thing for this layer, same thing for this layer, and then you do that over and over and over again. So you start out with totally random weights, and based on how things, what kind of predictions you get, you start adjusting the weights back forward. You start adjusting the weights to give you better results next time. So,
Sounds a lot like Kalman filter.
yeah.
Is that?
I don't know. That's an advanced question. I don't know.
So does that mean that each round of this, that you are, I guess this would be what your initial training looks like, that you are putting in the random weights and then comparing it to, or trying to make it predict values that you already have and see how accurate it is until it's close enough for your purposes, and then you start giving it new data?
So you usually look at all your data in one pass and then make the adjustments, and then look at the data again in one pass and make the adjustments. Now, what you do with when you're doing any kind of machine learning is you take your original data and you split it up into stuff the training set that you're going to use for training, and then some kind of validation set that you're going to use to measure how well your system is going to perform on data it hasn't seen. So you train on the training set over and over and over again. Now, there are some things where you actually break the training set up into little chunks. They're called batches. And then you train and you adjust on one batch, then you show it the next batch, you train and adjust on that batch, show it the next batch, train and adjust on that. And you just do that over and over again until the whole system settles down and gives you a good prediction. Okay? Okay. And then there are probabilistic methods. Probabilistic methods try to not give you like single values. Like, remember in the linear regression, we had one slope and one intercept is what came out of that. A probabilistic approach to that would give you a range of slopes that are likely and a range of intercepts that are likely based on the data it has. Because this method, it really could be like just anything like that. It really could go up and down like that. But we don't have that information in a regular statistics kind of way. We just get a number and a number. In a probabilistic method, you get a little distribution here. It's like, oh, it's probably around this area, and it's probably around this area. So it's really powerful for situations where you need some kind of confidence or some kind of error bounds or something like that. Okay? All right. So I have a notebook, and I'll try to do this really quickly so we don't spend too much time on it, just to give you some examples of how we would do this. Again, this is in Python, and if you haven't used notebooks, it's kind of just a web browser thing that lets you execute code in it. So I'm going to import my pandas and NumPy from sklearn, a function to split my data up into the training set and a test set, and then I'm going to use a random forest. So a regressor. It's a regression problem because I'm going to predict a price, a number, and I'm going to use the random forest algorithm to do regressions for that. And then matplotlib just lets me plot out numbers. Okay. Questions? So I'll run that. Then I'm just going to configure my plotting thing to make my plots a little bit bigger. And then I've got this CSV file of the King County housing data. I'm just going to read that into my data frame using pandas. Again, pandas is kind of this table kind of situation, so I can print out the head, which is the first few rows of that table. You can see I have an ID. I have the date sold, the price, the number of bedrooms, number of bathrooms, square foot living, the size of the house, and so on and so on. I can ask the data frame to describe the information for me. Just give me some descriptive statistics. So it gives me the counts. I have 21,000 IDs in there. The mean ID is 4.58, whatever. This is irrelevant. You wouldn't take a mean. It's just an ID. It's just a number. The data frame doesn't know that. But the mean price is important. $540,000 is the average price in this data set. But we can see the standard deviation of the prices is 367,000. So there's actually a lot of variation in the data. Minimum is 75,000. Maximum is 7.7 million. Same for the bedrooms and stuff. Like most houses are 3-bedroom. Some are as big as 33 bedrooms. I don't know where this data come from. I don't know. I just got it off the internet. I don't know. Same thing with the bathrooms. Some house has 8 bathrooms. Like this thing has 33 bedrooms, only 8 bathrooms. That's interesting. If it's the same house. Size of the house, the smallest one is 290 square feet. The biggest one is 13,000 square feet, so on and so on. So that's the kind of data we have. Okay. So for the purposes, so what we're going to do is predict price. We can actually predict anything. We could try to, based on the price, predict the number of bedrooms or something, whatever you want to do. But the most obvious thing would be to predict price. So I'm going to call that my y. Data scientists really like to use x and y as variable names. That just means this is the target, and then these are the dependent features that I'm going to use, or the features I'm going to use. So I'm going to take the price out of my data frame. That's my y. And then I'm going to take the data frame, and I'm going to drop the price, because I can't use the price to predict the price. I'm going to drop the ID, because the ID should be irrelevant. It should just be a random number. I'm also going to drop the date and zip code. There's probably some information you can get out of the date and zip code, but those are kind of those are data types that need a little bit more manipulation that I want to get into here. So I'm just going to drop them and just ignore them, pretend they don't exist. Pretend I don't know the zip code, I don't know the date. I drop the ID and I drop the price. And then I'm going to take all that and I'm going to run this through my train test split, passing in my x, my y, the size of the training set, the size of the test set. So that's going to break it up into 2 sets. I'm then going to go create my model, this random forest regressor. I'm going to remember the ensemble models use a bunch of smaller trees. And each tree looks like a small subset of the data, and then they make their prediction, and then all those predictions are ensembled together to make your final prediction. And then I'm going to fit. So that's what the random forest does. I'm going to use 50 trees, just because I felt like using 50 trees. And then I'm going to fit the data to my model. I'm going to pass in the training data, the training x and the training y. That all ran, and then I'm going to use the validation x to make predictions. And so now I've got predictions. And notice, and note here that this is the x validation. I have the true values for this. So now I can compare my predictions against the true value to see how well my model is doing. There's a bunch of statistical ways to make those comparisons, but I'm just going to plot it so we can see it visually. This is the true value, and this is my prediction for it. And if everything was perfect, in a perfect world, they would be exactly the same. So they would all be on one line with an intercept of 0, slope of 1. So if the true value was 200,000, then it would show up exactly here at 200,000. So we can see that it's not exactly a line, but they are kind of close together. So this is a pretty good predictor. A true value of 200,000 has a big variability of what the prediction is, but it's somewhere around 200,000. I could make this better, but this was like the fastest way to do this, to show you in the time frame we have. And we have some outliers. It's kind of interesting. Maybe we should look at the data and figure out what these outliers are, and maybe why they confuse the system. Maybe this is one of the 33-bedroom houses or something like that. Or maybe that house really doesn't exist or something. I don't know. But you can see very, very quickly we're able to build a system that makes predictions, and they're pretty good. You just need to decide if this is good enough for your particular use case. You might need this to be skinnier, but you might be like, hey, it's good enough. Now we know where to start, or we know that these houses go to one person, and these houses go to another person, and we're good to go. Questions about that? All right. This particular model also has this thing called feature importances, which is it's going to tell you of all those features we gave it, what did it find most important for predicting house prices? What would you find in the data set, in the features we've already talked about, what would you think are important features for this data set? Number of bedrooms, yeah. Square footage. What's that? On the waterfront? Okay. Yeah, so I'm just going to combine the numbers and the feature names and print them out in sorted order. So the grade was the most important thing. We don't know what that grade is, so it could be that grade is assigned after the house is already sold. So the grade could be cheating. I don't know. I don't know how we got that grade. So we'd have to look it up. We have to find the data set. The size of the house, so whoever said that was right. The latitude and the longitude. How close it is to Seattle is actually more important than anything else. That's what it turns out to in this data. The year built, the square foot in 2015. So the house could have been renovated or something. I think that's what that means. And whether it has a view of the waterfront, and then the size above basement, the living space above the basement, and so on and so on. So you can start getting a feeling for what the model is doing. and what kinds of predictions what features it's looking at to make its predictions. So if somebody said, hey, you're not giving me full value of my house is worth a lot more, you can then start looking at this and go, well, actually, we look at the grade, it's very important, and we don't really care about the number of floors, it's a 3-story house or whatever. So that's why we're making this prediction. Okay.
So that's how you can explain to them. You got a low grade.
Well, that's a start, I think. I think that's a start. Okay. So that's the notebook. And that's it. So, so I'm open for questions, and we can do whatever you guys want. I don't know how long we normally talk for, but I could talk about machine learning for hours. Hours and hours. Yes?
So you said that you are a consultant.
Yes.
So a new company comes to you and says, we want you to help us with some data.
Mm-hmm.
What is the process that you go through to decide which machine learning algorithm you are going to use? Is it based on the questions that they want answered, or is it based on how the data is set up?
So you asked me a very specific question, which is what model I would use, I think.
How would you decide? What's your process?
So it would depend a lot more on like external stuff. But I would say most things, like my favorite thing that you can use for most problems would be one of the ensemble methods. And there's something called a gradient boosted tree. That thing seems to work well no matter what. And it's easy to work with. The data doesn't need to be like super clean, or it's very flexible with the input, and it seems to predict really, really well. So that would actually be my first thing. But you should always have some kind of baseline. What's the simplest thing you could do? Maybe make the median prediction, maybe make the most common prediction, depending on what you want to do. Maybe try a linear model. The thing with the linear models is people like them because the coefficients are right there. They're very obvious. It's 3 times the number of the bedrooms plus 5 times the numbers of the bathrooms. It's 3 and 5. It's very clear. Whereas the ensemble methods, you get these features at the end, but it's a little bit less clear what the system's doing. So somebody comes to me, they have something, I would really spend a lot of time on the business side of it. Like, what is it that they really want to predict? Why? And then what about that do they want to predict? Do they want to predict that someone's going to buy or not buy, or do they want to predict the probability that they're going to buy or not buy? Because that's a different kind of problem. And then what kind of data do we have? And then given that data, I would then choose one of the ensemble methods, most likely. And then if they needed some confidence interval numbers, maybe try to use a probabilistic method instead. And if they had a ton of data and a good budget, then we'd do the deep learning approach. But the ensemble method is a really good place to start. A gradient boosted tree, just throw that at everything. Other questions?
When you're running data through all the different layers, so those multiple layers, you're doing the same formula on each layer?
Yeah, each node in a fully connected network like that. And there's a lot that goes into a neural net, deep learning. Each node does the same formula. It just has a bunch of weights. It's got some number of inputs. It's got a bunch of weights. It's going to multiply them all. It's going to add a bias. And then it's going to run that number through a nonlinear function. So just something that's going to be like a step function. And then it's going to output something. And that's all every node does. And it's the whole idea of running the data through and then using this backpropagation algorithm to figure out how the weights should be tweaked when you come back and you backpropagate all the corrections, all the changes, and then you run it through the data again. And you don't actually have to do that. Like there are a lot of frameworks that do that all for you now. You just have to know how to set it up.
Yeah, so for getting started into machine learning, is the best kind of route just to be working on programming and statistics and then just building projects to just kind of hone skills, or is there more to it that you can be doing?
No, I would say find a problem that you like or you're interested in. I mean, if housing prices float your boat, that's great. If they don't, then find something else. There's always something, predicting prices on farm equipment, predicting prices on Pokemon cards or something. I don't know, whatever it is that floats your boat, you like. There's probably some data set somewhere. And then I would take that data set and then start using these algorithms. And you can use a linear algorithm to start with, to try to use linear regression. And then I would say use the ensemble methods and learn how to use the ensemble methods. And then, and then you're on your way.
Just kind of keep building yourself up.
Yeah. Yeah. I mean, and it's helpful. Like a lot of people say, like, well, I don't like, or I don't know, I'm not good at math or statistics or calculus or whatever. You know, the more math you know, the more math that you know, the better, and the more comfortable you are, the better. But you don't need to be like some, you know, genius level mathematician to do this. So I mean, I find it helpful to understand what the algorithms are doing, but all the math is already implemented in these libraries, so you don't need to re-implement them or anything like that. But it is useful to know what they're doing or how they can fail or why they would want certain things. Yeah.
When did you start learning about machine learning and deep learning, and what was your
Like
career
100
path?
years ago. No, it really was. I started programming when I was in the Army a long, long time ago. And when I got out, I went to graduate school. I got my bachelor's in computer science. And it's weird, I really found it almost on a philosophical level. What I really found interesting about computers is that you could represent things, and then you can manipulate those representations, and they'll give you like some kind of useful answer at the end. So just think of like numbers. You have bits, and then you flip the bits in certain ways, or you have two sets of bits, and you kind of do this operation to them, and then that's addition. You know, that's like how much I'm going to get paid next week or something. You know, I found that like really philosophically really interesting. And then the next step beyond that would be AI. Like, what does it mean to know something? What does it mean to understand? What does it mean? So really from a philosophy point of view. So I started in graduate school. I got a master's, and I worked my PhD for a while. But then I realized I didn't want to be an academic. I just like being a graduate student. But I was going into debt, so I just became a programmer for a long time. And then the last 5 years or something like that, AI and machine learning has kind of revived. There's been a revival, so I've kind of gotten back into it since then. But I did start a long time ago.
Were you researching machine learning?
Yeah. But that was a long, yeah. We barely had computers back then. Yeah. It was an abacus paper.
So between all different libraries for like different languages or just competing libraries for the same language, like last time I looked at this, there were like 12 for Python, for example. How different do they tend to be, or are they mostly interchangeable?
I mean, that's an interesting question. I don't know exactly what you're getting at. Like, once you pick a language.
So I think a better question would be, like you mentioned, that you don't need to know the statistics that deeply because the math is already built into the library. So how different would the math be between all of these libraries? So if I try giving a bunch of different libraries the same data set, how different would you say like my answers would tend to be?
Do you mean different libraries of implementing the same algorithm or different algorithms?
Start with the same algorithm.
Yeah.
Simplify the problem a bit.
So some of the algorithms have a stochastic, or kind of like some randomness in there, because the way, like the random forest regressor, kind of randomly chooses columns and rows to look for each. I'm going to say there are 50 trees I'm going to build, and then it will randomly choose columns and rows for each one of those trees to look at. So since it's choosing that thing randomly, you would not expect even the same library to give you the same exact tree every single time. So in that case, then there is going to be difference. Even running this algorithm twice will give you different answers. Within different libraries, even if you didn't have that level of randomness, there might be some subtle differences, but you would expect the result to be very, very similar.
Okay.
Yeah. And each one of these algorithms have like a million options. So there's like lots of different things about how many trees, how many features it should use, how it should decide what feature to make the rule based, to base the rule on, like there's like an information gain, how much does this making this decision help me make my predictions later on. So there's a lot of stuff that goes in there. Anything else?
Out of curiosity, Jupyter, your preferred IDE for?
No, I hate Jupyter. No, Jupyter is fun because it's great for doing presentations because you can see it, you can run it, and it's really handy. I end up doing a lot of work in Jupyter because you can have a running system that you can then have it do something else without having to rerun everything all the time. So that's really handy. But with Jupyter, it's easy once you start messing around to like run things out of order, or to have a variable have an old value or something like that. So periodically you need to clear it and reset it and rerun it, and then move things into a more traditional software development kind of system. Anything else?
So when are you gonna talk about AI? Like what aspect? Is it gonna be in a different meetup?
I don't. Well, I don't know that we talk about general AI very much in any of the meetups. In one meetup we talk about deep learning specifically, and the other one we do the probabilistic approach to this. But I don't know that we talk about general AI so much.
You don't
specifically about that.
Okay. Are you going to implement that into the machine learning?
Add more talk on AI?
Yeah.
No, because I think that's kind of a futuristic talk. Like this whole robots that will understand everything that you want them to do is just not something. It's not something I can get paid for today. So I like getting paid today.
All right.
So you need to know how much you should bid on a house or something. I can help you there.
Okay.
Okay. Any other questions? Okay. Thank you.
Thank you.